Can you still hear me?
Yes, we can still hear you. So apparently we are now online again. So Eveliina, if you're ready, I can start the introduction.
Yes.
Okay. So, well, welcome back, everyone. So the second speaker will be Eveliina Peltola that will talk to us about boundary correlation functions in 2D critical model. So thank you very much for giving us this talk.
Thank you very much for the invitation. I'm very happy to open up this new year with the One World Probability Seminar. And I wish you all a healthy new year. Greetings from snowy Helsinki. So so you see from the slide that I have two affiliations, if you didn't know yet. So now I'm primarily in Helsinki, in Aalto University, which used to be the Helsinki University of Technology. But due to some merging, kind of analogous to Paris universities, they changed the name because some other universities merged with it. But I'm also working in the University of Bonn, so can find me occasionally in both places. I guess most often at home these days because of the pandemic. And I will be kind of continuing from what Hao left. So she was talking about the uniform spanning tree in the end. So I'm going to come back to it in a while. But first I want to tell you a bit of the general story of these, how to find these formulas for the crossing probabilities, and also a little bit about other correlations in critical models. So there are many predictions one can cook up from the physics literature, and then the task is to try to make them precise. So the main reference is this UST paper, but I will mention a bunch of other things along the way. All right, and also if you have any question, just feel free to interrupt me anytime. I don't mind. So as Hao explained, if we look at some critical lattice model, like the Ising model, in let's say 2 dimensions, we expect that if we take the scaling limit, so maybe there's some delta meshed graph, and we take delta to 0, so that would be a scaling limit. We expect conform invariance. So we expect some conformally invariant quantum field theory describing the limit. But of course, as we know, quantum field theory and CFT, they are not very well developed mathematically. So there's a big question mark of what that object is supposed to be. And you can try to look at some specific features in these models, like the curves that converge to SLEs. So that's been a big success in the last, 20 years or so. And also from SLEs, you can actually try to understand CFT a bit better. So here's this kind of triangle connections between these different theories. And in my talk, I will be a little bit heuristic. I will tell you when things are known and precise, and I will try not to cheat too much. But if you're confused, just ask, because there's a lot of kind of motivation from this not so well-known CFT world. But I'm trying to convince you that it's actually very useful when you want to answer questions for critical lattice models. So it's worth kind of trying to look into it a little bit at least. In general, so let's say if we are in the plane, if you look at any reasonable critical model, so Hao listed a few of them, we would expect some kind of convergence in the scaling limit. And then the task is to make sense of the convergence. And one way was to look at the interfaces. So this is a recap. What you find, at least in many models that have been proven, you find SLE curves. So in the picture, this is a simulation of the critical easing model that Hao already introduced. And here is maybe plus spins on these left and top sides, and in the bottom and right, minus spins, and you have this interface from the corner to corner, which is a random curve in the discrete. And in that case, it's known to converge to the SLE3. For other models that were listed in Hao's talk, we have a similar type of convergence result. There are also some open questions, so not everything is known. But there's a usual strategy for the proof. First of all, you need to show that you have this collection of random curves living on the lattice. So like in the picture here, I don't know, maybe gamma. So that's a random curve. It has some law. And the convergence over here is supposed to be taking place weakly. So in terms of the law of the curve. And on the right-hand side, there's the law of the SLE, which is very well known. So you don't need to know it for this talk, but it's something people understand very well. So you need to be able to say that there's a chance of convergence, at least along some subsequence. So that's a tightness property, which is quite kind of general for many models, and there are technical difficulties that one has to deal with. But then there's the more kind of insightful step, which is the identification of the limit. So if you have a convergence of a subsequence somewhere, maybe the subsequences have different limits. So you need to show that the limits are the same, and you want to understand the limit. So that's the identification. And already there, these observables developed by Smirnov and others play a role. Okay, so what I want to focus on more are correlations. And these are a little bit less geometrically defined, but let's see. Sorry, so I forgot the conjecture for SLE. So I will come back to this later. But we can formulate the conjecture in a way saying that this model where you have these interfaces that are forced to be there by some boundary conditions, like plus minus alternating. The boundary conditions are given by some correlation function. So that's a special case of a correlation function, kind of. And if you look at the physics literature, there's supposed to be a special object in CFT, which is denoted phi12. Don't worry about it. It's just a notation, which is sitting at some point x. We should draw over here. So when there's a curve starting at the point x on the boundary, that's supposed to be somehow generated by some CFT object that is not by any means well defined. It's just a formal object. And if you want to then look at a picture with several interfaces where also this crossing property question comes relevant, so you put these kind of points x1, x2, and so on the boundary, and you would look at a correlation of such objects. So I will try to tell you more about this during the talk. But that's somehow the very rough idea of how to, for example, try to guess formulas for these correlation functions that Hao was talking about. And a very useful tool, as we know, are martingales. And there's a specific looking martingale that comes up here. So I think the next slide has a little bit explanation why this comes up. But there's some function f that's unknown. Then there are some marked points that are basically time evolutions of these boundary points in my setup. And then, okay, some derivatives of conformal maps and some powers that are not so relevant here. It's just some explicit factor. And the time evolution comes from the Loebner chain. So I will show a picture next slide. Don't worry. The message here is that this expression, depending on time and all these marked points, that is supposed to be a martingale, at least up to some stopping time, for the growth of the SLE curve. And if that would be the case, we would actually find a differential equation that this auxiliary function has to satisfy. And this is exactly what Hao showed you. And if you look at some physics book, you will find that this weird simple phi12 field, actually its correlation functions have exactly the same PDE. So there's at least a superficial match between what you find from SLE martingales and what you find in this very sketchy conjecture in physics books. And the last bullet is about the fusion that was discussed for the metric graph GFF. So just for those of you who already are familiar with this, so if you want to have somehow several curves starting from the same point, let's say S minus 1, then there's an object that should correspond to it, which has the same kind of labeling, but with 1, S instead of 1, 2. That's some common notation in physics literature. But never mind the notation. Let's try to make sense of this. So how to understand the boundary conditions as a correlation function, and how is that related to these interfaces and SLEs, and finally, how do we get to these crossing probabilities from that? So to elaborate this a bit more, so here is now finally a picture of the growth of the SLE that you are probably already waiting for because of all the notation that I didn't define. So if you look at SLE in the upper half plane, starting from some point X and growing to infinity, let's say, at each time, you can map the initial segment or the hull, if it's touching itself, back to the real line and look at the future, which will be then an SLE curve in the image side. And you will have a driving function that's here called WT. And as you know, some of you at least very well, this is just Brownian motion times some speed for the usual SLE. But if you have some marked points, so here are some marked points, that will be a Brownian motion with a drift. So this is really hard to write with it. Marked points. So the driver satisfies some SDE involving a martingale part and a drift part. And the drift part is what we see when we put boundary conditions. And then these points over here will be the marked points where the boundary condition changes, maybe from plus to minus or something like that. And they also move according to this Loebner evolution. So we have a formula like that. And from here, you can calculate more easily, and you find the PD that also appeared in Hao's slides already. And this is a quite canonical construction, actually. So the reason why it works is the Markov property of SLE combined with its conformal invariance. So it's very specific to critical models, which should have this conformal invariance in the scaling limit. If you want to go off criticality, you need to do some perturbation of this. So it's not quite as somehow structured in off criticality. But for critical models, we have lots of structure, and this is kind of featured in this kind of CFT framework. So then, if you believe this kind of formal calculation, how marked points affect the growth of some SLE curve in terms of the driver, you find a PD, and if you look at the physics book and you believe that these PDs have something to do with these fields, the font is different, so this should be the same field as in the previous slide. You would somehow expect that in this wild conjecture about conform invariance, this drift object should be described by something that people write in this way. So the bracket over here is supposed to be some kind of expected value, but it might not be normalized to be a probability measure for these objects. So that's why it's we write bracket instead of just expected value. And also the right-hand side over here is not a priori well defined. So we want to make sense of it. However, we can guess some properties for it if we believe that the SLE growth is corresponding to this kind of field.
Sorry,
is there a question?
Sorry, I don't see the lowest part of this.
You don't see? Oh.
Maybe I don't know if it depends only on my computer. Not
I see.
The lowest part of the slide.
So what should I do to fix it?
I think I see the bottom part.
So there's a reference to Duplantier-Saleur and Bauer-Saleur in the bottom. Do you see that?
Yes, the bottom, only up to a certain point.
Oh, that is very strange. So, so no, certainly doesn't.
Yes, yes.
Okay, so let's go there. So you still don't see the whole thing?
I don't know because I don't see. I think there is something below, but I don't. Maybe if you reduce a little the.
So over here, there's upshot and this kind of question mark formula.
Yes, that I don't see. That I don't see.
You don't see. So
I apologize. I forgot to send the slides, but maybe you can download it from the chat.
I wonder how to, because this doesn't allow you to.
I mean, for my part, I see the complete slides. So.
So it's not a global problem, at least then.
Yes, I guess. I'm not sure.
Okay. So let me try to. I can do like this, and maybe then you see.
Yes, that is yes. Now I see.
Yeah. Okay. So I will pay attention to this. But so the upshot from here is that if we look at the physics conjecture, we would expect some properties to hold for these objects that are generating SLE curves. And these are exactly the things that come up in the crossing probability formulas. So if I go here somehow, what is the SLE affected by some marked points? So maybe here's a marked point. I call them Z1. Notation is very bad. Zn, here is GT, Z1, and so on. So they move, also move in time in this learner flow. So this object has to satisfy some PD, as we already saw in House talk. And somehow the upshot is trying to say that matching this with the physics prediction, we expect that some particular fields in the field theory are kind of corresponding to this object. And we can derive some heuristic from there. So that was the upshot from here. So we get from kind of SLEs and interfaces to correlation functions in this way. And in this example, the points are on the boundary, but they can also be inside the domain. But I will focus on the boundary case most of the time. Okay, so we'll get back to it, don't worry. So just as a general note, so about correlations. So there are many other types of correlations than what I'm describing. And to my knowledge, the mathematical results, there are some for various models. This is the critical easing model picture, which has the most complete description. You can calculate some for branches of the uniform spanning tree, maybe also in some other models. At least crossing probabilities you can calculate in percolation. But the point is that every model has kind of specific features that need to be used to deal with the technicalities. And so far it's been unavoidable. But from the general framework of this heuristic, we can at least see some common features that we expect. And then when we try to prove things, we need to go to the specific tools. And just to say something about the scope very briefly, this is maybe one of the most famous results on correlation functions, proven for energy density by Hongler in his thesis and the paper with Smirnov. Then this spin correlation that I already mentioned. This is originally by Chelka, Hongler, Izirov. And the same people have a more new paper, which has very general correlations for the critical easing model. So one could say that this model is very well understood when these points are spins, energies, or disorders of fermions or whatever. But it's a very particular model, and they use very particular techniques to do like that. So they again use the discrete holomorphic observables. They must be much more elaborate. So this is very difficult work, and I'm not able to kind of summarize it for you. So you can have a look if you're interested. I just want to mention that it's a very celebrated result for correlation functions, which can be related to what this physics literature and CFT books predict for the critical easing model. And you see it's quite recent from last year, from 21, for this kind of most general results to have been established. Okay, so let me summarize the properties that one often expects. So in the easing spin case, for example, there is a PD. I think it was first verified in a paper by Izirov. So it was actually somehow surprisingly hard to verify. And many other observables, meaning correlation functions, have similar PDs, especially those related to crossing probabilities. So you will see this kind of formula many times. It's a second order PD, which is homogeneous. So there's a first order derivative and no derivative with the second power. And here is the system. So for each variable, there's a PDE because it's describing somehow the same random variable at each point. And then there's some transformation rule under conformal maps that is very particular to this conformal field theory. But for us, it's just an additional constraint. So this can be used then to fix 3 degrees of freedom. So the 3 Möbius maps of the Riemann sphere. And there's some particular power of the derivative of the conformal map that is related to the critical exponents. So this is also something very general for critical models. And if you work in Liouville, I didn't look who's in the audience. course, you have this kind of PDs in Liouville theory as well. So this is somehow very, very ubiquitous in the CFT literature. There are, of course, other fields as well, but very often for questions related to random geometry, these ones are what come up, maybe because of the SLE martingale structure, for example. And now if you try to look at more general observables, maybe curves, several curves starting from the same point as for the metric graph GFF, you find the higher order PDs, which I didn't write down, but there's a hierarchy of them. Okay, so everything is somehow, at least you can guess stuff from here. So the conclusion is that we might be interested in these solutions to these PDs in order to solve problems in random geometry. And this has been indeed very successful in the last, I don't know, 6 years, maybe that was the time frame, thanks to also some classification results of solutions to these PDs. And somehow, I'm not going to talk about the classification because that's a very long story done by Flores and Kleban, but I will try to tell you how to find formulas for these solutions, because already if you have many points and complicated boundary condition, it's not clear at all how to solve them. And there's a very cute strategy to try to do it, which is the Coulomb gas, that Hao very briefly mentioned. And it works very nicely, as Hao said, for irrational values of kappa. So remember that we have this parameter kappa in SLE kappa, and in the critical models, it's enumerating universality class of the model. Maybe I should zoom again. And there's various degeneracies happening when this parameter is rational. And it's not somehow very destructive, but it's causing some anomalies and some linear dependencies in this framework. So the general results have to be taken somehow carefully. So it's best to assume that we are non-rational for the general framework, and then try to take a limit or use the idea and cook up a different proof for the rational kappa values. So this is more serving as kind of idea of how to find these, for example, the pure partition functions that Hao was talking about. And I listed lots of people in this reference list. Maybe notably, Julien Dupédat had worked on this already quite a while ago, 2006. He has paper on Euler integrals and something like that. And the commuting SLE paper, the kind of companion papers, where he was trying to solve these SLE pure partition functions. He found some other functions which are actually useful. He didn't unfortunately find the pure partition functions, but he already used these ideas from the physics literature. And we elaborated on, especially on some certain symmetry of a quantum group that I'm not going to talk about, just mention it here, with Kalle in a bunch of works. And that idea can be used especially for the uniform spanning tree question. That was part 4 in Hao's talk. So that's the main reason I'm bringing it up here, somehow how to get these Coulomb gas formulas for the uniform spanning tree crossing probabilities. Okay, so let me briefly describe the general strategy, because it's very nice. So first of all, so we have some differential equation of a function of several variables. So here's a function. And maybe for each variable, we have a differential equation. like for the pure partition function, there was a second order differential equation where the highest order term was associated to the jth variable. And then there were other terms. And due to a particular form of these equations, the following strategy works kind of nicely. So it turns out that there's a very easy solution for this kind of equation, which is just the product of differences of the variables to some powers. But that solution doesn't satisfy the other properties that we want. And the idea is to modify that solution. So that would be the small f, essentially. I will give you a formula very soon by adding some additional variables which are integrated over. And in order to find a solution to the PD, we need to check that the differential operator, which is explicit, annihilates this kind of ansatz. So we want to cook up an ansatz. And how to find it comes from some heuristic from CFT that I won't go into, but I will show you how it works. So suppose we try an ansatz like that, and we want to find a solution. So let's see, if the differential operator is explicit, and this one is explicit. I didn't tell you yet what it is. You saw it in house talk, actually. You can calculate stuff. So assuming everything is nice enough, you can take a differential operator and see what happens if it was acting inside the integral. And in this setup, what will happen is that you find a differential of some form. It's a quite horrible looking formula, but that's something you can find. And now if you apply it to the ansatz down here, so you just plug in the differential operator, you take it inside the integral by some analyticity that you hopefully it is true, as it will be in this case. And then here you insert the result of the calculation, which is an exact form. Then you use integration by parts. And if you've chosen the surface that you integrate over in a suitable way, so that it doesn't have a boundary, you will find 0, because you're integrating over the boundary, which is an empty set. Oh, no, I don't know if you see the calculation here. So it's a short, quite easy calculation. And it relies on the specific form of the differential equations and the specific form of the ansatz. But once you have that, you can prove that the ansatz gives a solution to the PDE, which is, what we want to do if you want to prove formulas for crossing probabilities, for example. So that would be a first step. Try to find a solution. And now, if we have ansatz, which seems to somehow be useful, there are many ways to choose it, because you can choose any integration surface gamma, which doesn't have boundary, and the same argument will work. I cannot choose any small f, so that's actually quite specific. But nevertheless, I have many, many functions which are solutions to this problem. And then I need to single out the solution that's relevant for my question in the random geometry. So for example, for a critical crossing probability of a critical model. Okay, so let me show a formula, because now it's quite heuristic. So this was here before, just shrinked. So the ansatz looks like that. Integral some function small f. Small f is a product of differences of the variables to some powers. That's maybe like a black box from physics, but I hope you believe me that if you do the calculation, this actually works nicely, and you don't even need to know where this is coming from, because it's a bit disturbing maybe if you don't. But here are some powers which depend on kappa, so it's a bit complicated. There's degree of the differential operator, which in our case is 2, if we look at the second order equations as for the crossing probabilities. If we look at the metric graph GFF that Ha was talking about, there might be a third order equation, so then the degree would be 3. Realize maybe you don't see it again. So alpha j's are some numbers depending on kappa and the problem. And alpha minus is also some number depending on kappa. And you see when kappa becomes rational, maybe some of these exponents might become also rational or something like that. Yeah, because there's 2 square root of kappa squared. So yeah, so kappa happens to be in the exponents. And there might come some problems. So I'm claiming that the ansatz with the explicit small f with a calculation gives a solution to the PD. For any kind of integration contours that are closed in a certain sense. And then one needs to find the integration contours. And that is the difficult part, really. This is kind of coming from some heuristics, but there's no heuristics telling us what kind of integration contours we can put. And for that, there are various techniques that you can use. You can try to guess, or you can try to use some structure. I think I won't go there very much. Let me just mention that that's the step 2. So first step is to find what you integrate over. So how to find solutions in general. And step 2 would be find the integration surface for which it doesn't have a boundary. So the integration by parts formula works. And maybe some other properties hold that we want, like there was asymptotics in the crossing probability question. And this is highly non-trivial to do. So that's somehow the main difficulty in solving these problems. But at least we have some kind of ansatz that we can try to work with. And just remarking that for the irrational kappa that we don't like so much because all our interesting models have rational kappa. There's some structure, so everything works very nicely. For the rational kappa, things work less nicely, but the philosophy is the same. And some things are analytic in kappa, so some things you can even try to analytically continue from the irrational region, but it's not quite sufficient. So lots of work is needed still after that. And Ha was highlighting that these pure partition functions, which are giving the crossing probability, they should be positive, or at least non-negative. Maybe they might be 0 sometimes. But from this formula, I had actually some, if I go back, here the small f is there in the bottom. So it's some holomorphic function of several variables, which has some monodromy. So it's not even single valued. So this is a terrible function if you want to study probabilistic questions, right? So it's actually really hard to check that these functions that you choose for the crossing probability question are actually real valued and positive if they are giving a probability of something. So that somehow this approach doesn't help in getting the positivity as such. So you need additional work. So that was the last line remark in this slide. You can see it. And the upshot here is that there is some kind of general strategy to find solution to the differential equations that we're interested in. It's quite complicated, as you see, but it's not that bad when you look at it It's just some kind of systematic way. And then the trouble is to find this appropriate solutions with appropriate additional properties. Okay. So this is what we can learn from CFT, and some of this we can make precise. Let me get back to the probabilistic problem. I think I started, so I have 5 more minutes. Right. So let me get back to the probability model, because there was lots of kind of heuristics. So I hope I didn't kill you yet. So the left-hand side is the uniform spanning tree picture, how I already showed it. The right-hand side is the Ising model. So that's maybe more familiar. So the question was calculate in the scaling limit all possible probabilities of all possible crossing patterns. And I'm going to be focusing on the uniform spanning tree picture. And of course, it's related to SLE. So first of all, there are these functions that come up. I think I will, I want to jump to the model because I think it's better to have the concrete model. So the uniform spanning tree model. And the simplest case was take a graph, take a uniformly chosen spanning tree. It's blue in this picture, if you see the colors, with wired boundary condition over here and free boundary condition on the rest. And then the red guy is the dual tree. And then there's a green path, which is the Peano curve, which converges to SLE8. So that was the simplest setup of the model that was already mentioned. And now the point is to take more general boundary conditions and ask how to find crossing probabilities and use this differential equation framework for the solution. So I think Ha already described the boundary conditions pretty well. I have some pictures here. So in the top one, beta is the boundary condition. So it's telling us how the external, the points are wired externally. So here there's wired in between 1 and 2, then between 3 and 4, and between 5 and 6. And the rest are free. And you have then several Peano curves and several possible crossing patterns. In the bottom is less simple. So here's additional wiring of the segment between 3 and 4 and 1 and 2. And you can label it by planar pair partition. So this beta is living outside. It's telling you how the boundary conditions look like. So here it's like that. And then inside there's alpha, or it was called A, which is a random connection event that I haven't drawn. So inside here, there's the model and something happens there. And now the main result was, let me show it, that if you look at the limit of any connectivity inside, which is alpha, with any boundary condition outside, we can find it. And it's given by a ratio of 2 things. And the 2 things are exactly this kind of Coulomb gas integrals I was trying to describe you for this kappa equals 8 case. So that's why I went all this heuristic nonsense to try to tell you where the formulas for these guys come from, because it's quite mysterious otherwise. So the normalization factor is related to the boundary condition. And the numerator is related to the crossing event. And the numerator is the pure partition function that was already discussed quite a lot. So it was having certain properties, including this partial differential equation. And the normalization factor also has similar types of properties. And one can write formulas for both. So I will show you maybe a formula slide with formulas, and then I will stop so I don't go so much over time. So this theorem is about the interface, but we already saw it. And this is also about the interface. But here are the formulas. So the formulas for the function that gives the boundary condition. So for 4 points, 2 curves, it's a hypergeometric function. This is actually very well known. It's already appearing in earlier work by Hao and the students. So the fun starts when you try to find the general formulas. And this is also something Hao showed briefly, I think. So there are these powers of differences of the variables. Some of them are integrated over, and then there's the integration contours. That was written down in one of Hao's slides a bit more precisely. So it depends on this external boundary condition beta, which is explicitly determined. And one special case is already in Julien's work. And the way to somehow guess this guy is the Coulomb gas approach, because this guy should satisfy the differential equations. And this is the integral ansatz for the differential equations. And these powers over here depend on, so here's power 1, so depend on kappa being equal to 8. And then you can find, with some combinatorial argument, the pure partition functions, which were giving the crossing probabilities. Maybe I should zoom again. So there's a combinatorial matrix M, which needs to be inverted. And you find the Z alpha, which are the pure partition functions from F beta, which are the partition functions for the boundary conditions. So you can solve this problem using this invertible matrix. So the Z alpha is kind of explicit, but it's a little bit complicated because there are all these coefficients in front of the F betas. And F betas are more kind of nicer to write down. And just to maybe end. So I want to show you the asymptotics. Need to find it. There. So I'm showing for the Z alpha. The Fs have a similar asymptotics. So that was already also in Hao's talk, but just to come back to it. So one of the properties for these partition functions was asymptotics when 2 points go together. So here at some place jj plus 1. And then depending on the pattern, either this curve between the shrinking points just disappears and you get the function with less points. Or then in this case, you get something else. And there's a different normalization. So the key thing for the SLE8 that's different from before and different from the usual CFT framework is that we have a logarithmic correction here. And on the other side, we have just the power. And here's some combinatorial expression, which is basically saying that if I draw here, so I'm shrinking these two. So they kind of become one. So this is the fusion again. And okay, so that's the real line. They become 2 curves from the same point. But if you know that for the uniform spanning tree piano curve, which converges to a variant of SLE8, depending on the boundary conditions, that's a space filling curve. So it's going to visit every point. So actually, this kind of fusion that it's visiting this point, then they go somewhere. It kind of does nothing. So you see here that the limit doesn't depend on the point where you shrink. So Xi is the shrinking point. This is a special feature of kappa equals 8, but it's kind of maybe peculiar. And there's an explanation for this phenomenon in the CFT literature. I think I won't go there unless you ask. You find something in the slides. So I think I will stop here, and I'm happy to explain more about something if you have a question.
Well, thank you very much for your talk. So we have time for a couple of questions. Well, I guess more than a couple, but we have time for a few questions. So if someone wants to unmute himself or write down the question in the chat.
Oh, and I don't see the chat, so please tell me the questions from there if there are any.
May I ask one short question?
Yes,
of
go
course.
ahead.
Okay, thank you. So in the construction of the small f functions from the Coulomb glass literature, is there any problem? I do not know the literature in identifiability. Would it be possible to get different f functions? And would this in any way affect the solutions to the differential equation and the results? Because you showed the one here, yes, one form of
Here.
small f.
So heuristically speaking, I think if you look at the particle equations, so I haven't given you the general formula, but I gave you the second order equation. It's the same as in Hao's talk. The function has to have this form, and these exponents have to be a certain type so that you find a solution. And a rigorous answer in the second order equation case, when kappa is less than 8, so it doesn't apply to the uniform spanning tree, it applies to all the other models that Hao was talking about. There's a uniqueness result that the pure partition functions are the unique functions with certain properties. So I think there's no choice for this, what this f can be.
Okay, thanks. Thank you.
Is there another question?
Hello. May I ask a question, please? Okay, thanks. Just, Eveliina, could you comment on a bit more on the log correction in your last slide?
Yes, happily. Let me find it. So it's a bit small. So let me give you the kind of heuristic first, because I think that might help. Or yeah. So I was trying to explain that in CFT language, SLE curve is corresponding to some certain type of field inserted at the point where the curve is growing. And then you can look at the asymptotic of 2 points going together. And if you look at the CFT literature, there's a prediction of the asymptotic, which looks like that, with particular powers that are depending on kappa. There's a lot of formulas, so don't worry. It's something explicit. So this we saw in Hao's talk, I think, and this is another exponent. So this is the generic case with no logarithm. But now, if you go to rational kappa, especially kappa equals 8, for example, you'll find that these exponents are the same. So they are, let's see, like -1/4, I think. So they coincide, which kind of suggests that these two pieces, which are supposed to be independent objects, they have the same kind of rate of happening. And somehow that's one reason why a logarithm appears in the other one. So instead of this kind of asymptotic property, so this is like a Frobenius series, if you wish. So it's with quotation marks. You must allow not only power laws here, but some more general functions which can have the logarithm. So maybe that's a heuristic why this comes up in this case. But maybe did you mean more in the uniform spanning tree case as such?
But if you see something else from your approach, yes.
So from our approach, we can prove, so this is the generic case I skipped, but you already saw in Hausdorff. So in our approach, you can calculate this explicitly because these are explicit. So these are linear combinations of the integrals of Coulomb gas type. So you can make a calculation and you will find this result. That's kind of part of the theorem. And yeah, then you find the other one as well from the calculation. And these are additional properties. So to my knowledge, they cannot be used to determine the functions. So there was a theorem for kappa less than 8 that these functions can be determined by this kind of asymptotics. But this theorem fails when kappa becomes 8. So we don't have this uniqueness at our disposal. And this is an additional property. So here, yeah, maybe you see here is the same exponent in both,
Yes.
but the other one has a logarithm.
Yeah. So you find that purely from the Coulomb gas integrals.
Right. So this, yeah, exactly. So Z alpha is something like sum over beta of these coefficients, which was inverse of the meander matrix. Probably know what that is. And there was F, and F was an explicit integral of just one explicit contour over beta, and the explicit small f. Yeah, and I don't know if how is still there, but I don't have an interpretation from the probabilistic model as such, somehow why there's a logarithm here. But there's some peculiarity happening in the fusion because somehow the fusion is actually the same if you look at the curves, because here what happens is that you shrink this interval and there's a curve between them. It becomes very tiny, so it disappears, like Hao was explaining very well. While in the other case over here, so the curves go different ways, but now they merge. But because our curves for the SLE8 are space filling, this also disappears. So actually it doesn't kind of matter because we know that the curve will visit this point at any in any configuration. So somehow, I don't know if it's very clear, but the interpretation for the interface somehow has no difference between these cases because the curve is space filling. So that's kind of maybe the probabilistic reason why these cases only differ by a logarithm. Does it make sense?
Yes, thank you.
Thank you.
And maybe we have time for one last question. Well, if there is no more question, then let's thanks Eveliina and Hao again for their wonderful talk. So thank you very much for these talks. And so thank you all for coming to the seminar. So next week will be a pair of talks by Guillaume Sebron and Camille Mal on non-commutative probability and random matrices. Sorry, not next week, but 2 weeks from now. So if you're interested, please come.